To develop the formula for surface area, we're going to consider a surface R of UV. I'm just going to say right now, folks, if you hear background noise, someone's using a power washer outside. I have no control over it. So my apologies for that. Now we're going to consider also a region in the UV plane. And let's say that there's a little rectangle in the UV plane that maps to a patch on the surface R. The UV plane will say that the width of the rectangle is delta U and the height of the rectangle is delta V. Now recall that the partial of R with respect to U is equal to the limit as delta U approaches 0 of R of U plus delta UV minus R of UV divided by delta U. This implies that the partial of R with respect to U times delta U approximates a delta R holding V constant. And we can consider this on the surface by they're holding U constant here. We have kind of a delta R and here a delta U. We can likewise say the partial with respect to V of R times delta V approximates a delta R holding U constant. Now with the way I've drawn this, that's a little bit harder to project on the image. But what we're after is the surface area of the surface R of UV. So we're actually going to consider a parallelogram on the surface of R. Well, not exactly on the surface of R. It's got one corner on the surface of R, we'll say. And the parallelogram is formed by two vectors. One of them is RU times delta U, and the other is RV times delta V. And we're going to approximate the area of the surface by using these parallelograms. You probably know where this is going. The area of the parallelogram on the surface approximates the area of the patch on the surface, which is given by R of U of V, and the patch would be the blue portion here, and the surface is given by uppercase S there, and is approximated by the magnitude of RU delta U cross RV delta V, those being the vectors that are forming the parallelogram. Because of how cross products work, properties of cross products, we can actually factor out the delta U and delta V, and we end up with the magnitude of the partial of R with respect to U cross the partial of R with respect to V times delta U delta V. Based on this, forming a Riemann sum and using the familiar limit process yields the following definition. We will define that if a smooth parametric surface S is given by the equation R of UV is equal to X of UV I plus Y of UVJ plus Z of UVK, where U and V are ordered pairs in a domain D. I said domain D, I really just mean a region in the UV plane D. And if S is covered exactly once, as the points U and V cover D, then the surface area of S is A of S is how we write it, and it's equal to the double integral over the region D of the magnitude of the partial of R with respect to U cross the partial of R with respect to V times dA, where the partial of R with respect to U is equal to the partials of the components. So the partial of X with respect to UI plus the partial of Y with respect to UJ plus the partial of Z with respect to UK, and likewise the partial of R with respect to V is the partial of X with respect to VI plus the partial of Y with respect to Vj plus the partial of Z with respect to Vk. k. That we're going to put into a box. If it turns out that S is given by z, which is a function of x and y, then we can use that x is x, y is y, and z is f of xy. Then we would have that the partial of r with respect to x is equal to 1, 0, then the partial of f with respect to x, and the partial of r with respect to y would be 0, 1, partial of f with respect to y. And the cross product, rx cross ry, would equal ijk, 1, 0, partial of f with respect to x, 0, 1, partial of f with respect to y, and that cross product turns out to be negative partial of f with respect to xi minus partial of f with respect to yj plus k. So the magnitude of the partial of r with respect to x cross the partial of r with respect to y turns out to be the square root of 1 plus fx squared plus fy squared, the squares of the partials. Notice that this is kind of like a 3D analog to the arc length formula in a previous section. If we disregard the partial of f with respect to y squared, we have the square root of 1 plus the partial of f with respect to x squared, and that agrees exactly with an arc length formula from a previous section. Here, though, we've got a two-dimensional input, in this case x and y, and so we have to take into account that additional dimension in this formula for surface area. For a surface of revolution, say f of x, x going from a to b, and the surface or the curve is being rotated about the x-axis, we use as the parameters x equals x, and then y equals f of x cosine of theta, z equals f of x sine of theta, and we let theta go from 0 to 2 pi. And this should bring to mind r cosine of theta, r sine of theta, where our r is variable and depends on the function value f of x. It is easily verified that the area of the surface, which in this case would be the integral from 0 to 2 pi of the integral from a to b of the magnitude of rx cross r theta dA, agrees with the formula for the area of a surface of revolution given in an earlier chapter.